Hi, everybody. I hope you're doing well. In the present lecture, I will discuss functionals and functional derivatives. It is a very important subject, mainly in statistics and statistical physics. It's very important, and mainly in quantum field theories. The so-called Feynman path integrals make use of the so-called functionals. So we need to answer what is a functional. And in this lecture, I will adopt not a formal mathematical approach, perhaps. So excuse me if you are more interested in a more formal approach to these questions. But I'll try to give you a intuitive understanding of what is a function. Well, so from a mathematical definition, a functional is a mapping. It converts a let me say a functional. It converts some space uh, of real numbers in n dimensions to a real number, or perhaps a complex number. Okay, it could be, for instance, complex here also, but a complex in n dimensions, it corresponds to perhaps reals in 2n. So I will discuss in brief this notation here. So if you have an example, a typical example of a functional, if you pick up an integral over some interval a to b of a function phi of x dx, it gives you a number. Okay, so a definite integral is a functional. Uh, this picks up all the values of the function phi and produces a real number if this function is a real, but it could be a complex. So a complex function produces a complex number. So it is a mapping of a vector space in n dimensions, real numbers in n dimensions, and it produces a single real value. Okay, so this is from a mathematical perspective what is a functional. Okay, but I'll try to give you a more perhaps intuitive way of thinking about functionals. So let us consider a function. Suppose you have a function of a vector r. Okay, this function depends on the number of dimensions of this vector here. So r is composed of x1, x2 till you reach the nth component. So r has dimension n. Okay, and this is a function of x1, x2, and so on, xn. Suppose it can be, for instance, for a very simple example, a summation of xj, example here, to be concrete, xj squared. So you are calculating the Euclidean norm of this vector r. You are summing over the squares or the values from j going from 1 to n. It gives you a number, a scalar. And in this case of real vectors, it gives you a real scalar. So this is a function, a scalar function, okay? So it's a scalar function in this sense. So you have as an argument of this function here a set of numbers, a vector valued argument, okay? And this vector, the, the slots here in this function, these components of the vector are indexed by discrete integers or integers, which is a discrete index, okay? So you have a function of a set of parameters, let me say xj, and j assumes this is the index, assume values among the integers, okay? So among the integers. The index is discrete, okay? This is very important. But what happens if we try, for instance, to take n going to infinite and the index not a discrete number anymore, but a continuous parameter. So in replacement of f of r, which is f of x1, x2, and xn, we need to replace by an f of a function, suppose a function phi, corresponding to this, or let me use the same notation here, x of an index alpha, but alpha becomes a continuous parameter. Okay, so you're replacing a set of numbers indexed by discrete numbers by a discrete index and converting it to a continuous index, which makes this x here, which corresponds to this vector here, into a function. So this is a function of another function, okay? But now, if we take these steps, the summation becomes an integral. And this parameter, x squared, becomes a function of the index alpha. Otherwise, it will be a discrete index, but now it's a continuous parameter, and you need, in replacement of the summation, you need to integrate. Okay, so in this sense, from some alpha 1 to alpha 2, okay, in some interval here. So in this sense, a functional could be considered a function of a vector in the limit where the dimensionality of the vector space is infinite and this space is is continuous. Okay, it is the components of the so-called vector are indexed by a continuous parameter, which makes this vector here a function of some, now a continuous index, making it a function. Okay, so in this example, you are converting a summation into an integral, and an integral produces a number. The result of it is a number. Okay, I don't know if it is clear, but I could think about A functional, this way, intuitively, I could think about the functional in this way. So you have a function of a given set of numbers. Let me use phi here, indexed by discrete labels, discrete indices. You make these indices phi of j, this j going from discrete to continuous. This way, uh, these phi j's become a function of some alpha parameter, which assumes values in a continuum. So j 1, 2, 3, 4, and so on. Perhaps you could use negative indexes also. Okay, so it could have pick up values in the integers. Okay, but now this alpha becomes a real number. Okay, so alpha belongs or are in the set of the real numbers. This index becomes a continuum, and this, which is n-dimensional because the set of numbers I need to plug into this function is finite. Okay, phi 1, phi 2, phi n. Now I need to insert an infinite number, which is this phi. Okay, this object becomes a function in a vector space and indexed by a alpha, which is a continuous parameter. So you could think about each of these numbers as being directions. Okay, so you have the direction 1, 2, 3, 4, and so on until you reach n. Okay, this could be just points in in a straight line. Okay, so set of points here. Let me just use 1, 2, 3, 4, and so on, which I could represent as a vector, which would be orthogonal to any of the others. A vector 1 in a Hilbert space, for instance, a vector 2, and so on. But now I insert more and more points between 1 and 2, and 2 and 3, and so on. And it becomes, this would be j. Now it becomes a continuum in the parameter alpha. Okay, so it's a limiting process for which I take discrete values, take the limit to n going to infinity, and a very dense set of points here displaced by some delta of alpha. And now I have a continuous index. Okay, so to this index I would consider the value phi 1, to this phi 2, and so on. Now I have a phi of alpha 1, and between alpha 1 and the endpoint here, phi of suppose alpha n, I will have an infinite number of values or infinite set of values indexed by a continuous parameter. So here I have a phi of alpha. Okay, and this, which otherwise would be a scalar function, now becomes a function of an infinite number of degrees of freedom. Let me say this way, this now becomes a functional. This is a functional. Okay, so okay, you have a mapping from space Rn in n dimensions to a real number. Okay, and in this case, you have a single phi here, but if you could think about this phi as a vector, it is a vector phi. Let me represent it as a vector, which in the discrete scenario would have components phi1, phi2, till you reach the dimensionality of the space. And now you introduce a continuous label. So phi1, between 1 and 2, you have infinite number of allowed values for phi. And 2 and 3, another set of infinite numbers. And this becomes very dense, and it becomes a function because this phi1 I represent as phi of alpha 1, but between alpha 1 and alpha 2 there are infinite numbers of allowed values for this index. In other words, I am replacing an index by an argument of a function. Okay? And a functional produces this. Okay, I here in this function I insert a vector here, a collection of numbers, a vector indexed by the label j, but now we have instead of this discrete j, we have a continuous alpha, and this set of parameters becomes a, a vector with an infinite number of components. Okay, so in Hilbert space I could eventually attribute to each of these points here in this straight line, I would attribute a vector in a Hilbert space, which was a discrete space, now becomes a continuous space with n going to infinity, and between 1 and 2, an infinite set of other directions, between 2 and 3, an infinite set of other directions, each of them orthogonal to the others. Okay, and in this case, this is a functional which produces a number. The result of this is a number. Complex valued or real valued, it depends on the nature of this phi. If I pick up a complex valued function, and in certain cases it could produce a complex number here. Okay, so this is a function. Let's go back to the previous example. We would have a function of a vector phi1, phi2, and so on. Which could be, suppose these are complex numbers, and a collection of complex numbers, which produces a complex vector, suppose phi1, phi2, and so on, till we reach the dimensionality of the space. And the modulus of this vector produces a real scalar. So it's summation of the modulus phi j squared from j going to from 1 to n. Okay, but I will take the limit of n going to infinity, and between two of these numbers I insert more numbers, more and more numbers, until I reach a point where j must be replaced by a continuous parameter, a continuous index, and in this case phi j becomes phi of alpha. Okay, and the the summation in the limit, in this limit, where the index becomes a continuous parameter and the dimensionality of this vector becomes infinite, this summation becomes an integral of the modulus phi of alpha. I need to sum over all the indices, which means integrate over all the alphas, okay, from the alpha 1 corresponding in the discrete case to this one to alpha n corresponding to this n here, okay. So I have an integral. An integral produces a number. In this case must be a real number, okay. But if I remove the restriction of the modulus of the complex number, if this belongs to a complex n-dimensional vector space, if I remove modulus here, this will become just a complex number squared integrated over all the alphas allowed, and this becomes, as a result, a complex number, okay? So a functional could produce a real number or a complex number. In this example here, it produces a real number, right? This is the case. So, in this sense, in this intuitive sense, a, a functional is just a generalization of a scalar function, which admits as its argument a set of variables, a set of numbers, okay? So a set of variables. In this case, you have inserting numbers here for phi 1, phi 2, and phi n. It produces some number. It's the machinery here, it's a scalar function, which produces a number. Here I have another object which produces a number. But in this case, the input has a continuous parameter, a continuous index for the allowed values of phi. Okay, and this is, in this case, we call it a function. Well, the simplest example of a functional is a definite integral. Of course, it's the simplest example. Well, now, if you want to calculate for a function, okay, for a function, if you want to calculate a derivative, so derivative of a scalar function in the context of multivariables, I have a function f of phi 1, phi 2 to phi n, and I want to calculate the derivative with respect, for instance, to phi 2. It is a partial derivative with respect to, suppose, a phi j here of f, which is a scalar. This is a scalar. And I'll represent this as a vector, phi vector here. So I will take the limit for some epsilon going to 0. I'll keep fixed all the phi's except that one which is being variated. Okay, so I'll divide it by the epsilon. Okay, the vector phi plus some epsilon delta ij summed over all the directions a sub index I here. So this delta here represents a Kronecker delta. Okay, delta ij is 1 or 0. If I equals to j, it is 1, and it is 0 if they are distinct. Okay, so this represents the direction in this vector space here in this sense. Okay, but I'll need to subtract the function phi here. Okay, this is a derivative for multivariate calculus. Okay, if you have a function of many variables, not just one variable, you need to calculate the derivative. It is a partial derivative because you're making the variation of just one of the variables. In this case, some phi sub index j. Therefore, your vector here would become, suppose, the vector, the new vector. This all this I will call phi primed. Okay, this vector phi primed corresponds to the original vector phi plus some small amount of deviation from that vector, but in the direction of j. Notice I am summing over. It is corresponding to summing over all the i's here. I am using Einstein convention here of summing over repeated indexes. And in this case, only in the direction of j, which is being variated, some amount epsilon will be summed to this vector here. So because of this summation produces some small variation in the direction j. So if you write it explicitly, you have phi 1, phi 2, and so on. Suppose this is the phi j. Phi j, you'll add up some small amount, an infinitesimal value epsilon, and then you reach the last value. Okay, this j would be 1 or 2 or 3. So if you choose 1, you add epsilon to phi 1. If you choose 2, you add epsilon to phi 2, and so on. And then this is the definition of a derivative for a scalar function. You pick up the function with a small displacement in the direction which you choose to variate, minus the original function divided by that small amount epsilon. This is the definition of derivative of a scalar function, okay? But now, what happens if this j parameter becomes a continuous parameter? So let us see how functional derivative emerges from this definition. So how functional derivatives emerges from taking j to an alpha, a continuous. What happened in this case? If we instead of having a vector indexed by a discrete index, now we have a function, which means j becomes a continuous parameter. What happens in this case? Well, first of all, I suppose you are well aware of what happens to this delta function. Okay, it becomes a Dirac delta because the continuous version of the Kronecker delta is a Dirac delta. So discrete, we have a Kronecker continuous, continuous. Okay, we have a Dirac. Suppose the index I was using alpha, so alpha minus beta in replacement of I and j. So this is Kronecker, this is Dirac. Okay, this is a Kronecker, this is a Dirac delta function. Remember, the Kronecker, it is 1 or 0. According to I equals to j, is 1 or 0 if I is distinct from j. And here you have something like infinite or 0 for alpha equals to beta or alpha distinct from beta. Okay, so this diverges at exactly the point where alpha equals to beta. And it could be taken as the limit of some discrete set of parameters divided by some delta alpha here in the limit where delta alpha goes to 0, and this alpha here is I times delta alpha, and j is beta. This beta is j times delta alpha. Okay, so this becomes a Dirac delta. Okay, so alpha corresponds to I delta alpha, and beta is something related to j delta alpha. It becomes, if delta alpha becomes an infinitesimal, this indices becomes a continuum parameters, and you have a Dirac delta. Okay, so this is it. Well, we have to modify a little bit the notation. So in replacement of partial derivatives, we have functional derivative of a functional of a set of numbers which corresponds to a continuous function, perhaps. Okay, so this phi here, which in the discrete case would be a vector phi1, phi2, phi3. Now it's a function phi of alpha. Okay, so this is it. Suppose this is phi of alpha indexed by alpha, and I want to variate with respect to some specific point. Just like in the discrete case, I want to calculate the partial derivative with respect to some phi j. Now I want to see what happens to this functional. Okay, if I change a little bit in the point beta, in phi beta. Okay, I was changing phi j, but now the phi j must be replaced by some other object, a function which depends on a continuous parameter. Here it is discrete in the case of partial derivatives. And now we can take the limit for an infinitesimal change, epsilon going to 0, But now I don't have a scalar of a finite dimensional vector phi, but an infinite dimensional vector. I'm calling it a vector or a function depending on the continuous parameter alpha. So I need to replace here by f of phi of alpha. It depends on alpha in the index alpha. But at the point beta corresponding to the index beta, I will introduce a small variation, delta alpha minus beta. Okay. So in exactly for exactly the phi of beta here, I am introducing a small variation, epsilon, okay, minus the functional evaluated at the previous distribution or the previous function phi, okay, and it is the same as for a partial derivative. I need to divide by this small infinitesimal. This it's redundant to say small infinitesimal, okay. For this infinitesimal value epsilon, I need in the end to take epsilon going to 0. Okay, so it's infinitesimal. Okay, so notice in the previous case, I would have a discrete set of values. Suppose phi 1, phi 2, phi j, phi n. I have a discrete set of values. I am representing here the lengths or the strengths of each component here. But today I am adding up a small epsilon. A small epsilon. This epsilon produces here some phi j plus epsilon. And I need to calculate for partial derivative, I need to calculate the function evaluated at phi 1, phi 2, phi j plus epsilon minus the original set phi 1, phi 2, and so on, and divided by this epsilon, by this amount epsilon. In the end, I take the limit where epsilon goes to 0. Okay, this is a partial derivative. For the case of functional derivative, I don't have a set of values indexed by a discrete index. Now I have something like a function. Okay, so I have a function here. Now, okay, I have a function. This function indexed by the parameter alpha. So phi of alpha in replacement of phi of subindex j indexed by j, I have a function of alpha because the index becomes a continuous parameter. And at some beta, suppose this is beta, at some beta, I need to produce a variation. So I will produce the same function, but at this exact point, I will produce a small variation here, which corresponds to phi of beta, the original value, plus some epsilon delta of alpha minus beta. So this, because epsilon is 0 and this delta at exactly beta becomes infinite, this is a finite amount which produces at exactly this point a small variation of this continuous function, and otherwise it is the same function, and I need to calculate the functional of the original phi of alpha plus this change exactly at beta, which is this change here, minus the original function. And of course, take the limit, epsilon going to 0. Okay? This is the same as a partial derivative. But in the case where now beta becomes a continuous parameter, or in other words, we are replacing j, which is a discrete index, by a continuous index, which makes this phi of j a component of a given vector of variables phi of phi1, phi2, and so on, into a function. I could think about a function as the value of the function at a given beta as the component of a vector in a continuous infinite dimensional space where each point corresponds to a direction in this space. I could construct a Hilbert space about related to this line here, to this straight line here. I could construct a, a vector space attributing or mapping each point to a vector in a Hilbert space. For instance, in quantum mechanics, it's more important to consider Hilbert space, but perhaps another kind of space. Okay, so I ask you to excuse me if I am not being too much formal mathematically, or even uh, perhaps correct from the mathematical point of view. But I'm trying to bring you a intuitive notion of a functional derivative. Okay, if you have a scalar function, you have for a multivariate calculus, you have a function of a set of parameters, which I could just write f of phi j. If you replace this discrete by a continuous index, you'll have a functional, typically a functional, okay, which has an infinite set of parameters as the input. Okay, you have a function as the input at this slot. A distinction from function is when you are defining a function, you use these round brackets here. And when you are defining a functional, which gives you the idea of having an infinite continuous index for the components of this slot here, this argument, this vector here, you use a squared bracket. Okay, so squared brackets for functionals, it is the notation. For functions, you use this round bracket, and for a functional, you need to use a squared bracket. Okay, so this is it. This is the idea of functional derivative. It is a derivative, but since the argument now corresponds to having a continuous index, the values of phi are indexed by a continuum or a continuous index, you need to just adapt a little bit the definition of partial derivative. So this is a functional derivative, which has nearly the same form, but now you replace the Kronecker delta here by a Dirac delta, but the epsilon going to 0 is the same, and you need to take the functional calculated at a small variation minus the original functional divided by this epsilon, which is an infinitesimal and you need to take the limit at the end. Okay, so let us consider a few uh, examples here, or one example here. Uh, let us calculate okay, let us calculate the functional derivative of this. Suppose I could integrate from minus infinity to infinity here with no loss of generality here. Okay, so let us calculate the derivative of this function. Sorry. Well, first, if I have a functional or a function in the sense of a multivariate calculus, suppose I'm just summing over phi 1 plus phi 2 plus phi 3 plus phi 4 and so on till I reach the end component of this vector here, which has n components, phi 1, phi 2, and so on. Okay, suppose we have this. This is just the summation from j going to from 1 to n of phi j. Okay, this is the discrete version of that functional. Okay, and this is multivariate calculus. If I want to calculate the derivative of this function with respect to, suppose, phi 4, in this case, phi 1, phi 2, phi 3, phi 5, and the others must be taken as independent variables from phi 4. So if you calculate the derivative of this thing here, you have derivative of phi 1 with respect to phi 4 is 0, phi 2 with respect to phi 4 is 0, and so on. The only one which has a non-zero value is phi 4, which produces the derivative of phi 4 with respect to itself, producing 1. Okay, so this is for a discrete case. Okay, this is the case for a discrete case. This uh, produces the desired result. But this is for the case of multivariate calculus, where you have a discrete set of inputs or an argument composed by a vector indexed by a discrete index. Okay, but let's use the definition of derivative of functional derivative to this case. Okay, so I'm trying to calculate the derivative with respect to some phi, which I will change at some point y. Okay, so this is the functional. This is the functional. It's an integral. I want to calculate what happens to the value of this integral. It measures this. If you have an integral and you perturb a little bit the integrand or the function which is being integrated, you make a small perturbation at some point, the point y in this case, some arbitrary point y. What happens to the value of this integral? How it changes? So a functional derivative measures that. In the same way as the derivative measures how a function changes um, with respect to some direction of space. Okay. In this case, you are calculating how this functional changes by a small amount of variation of the argument at some index y, some point y. Okay. It is easy to do that. It is the limit where epsilon, the infinitesimal, goes to 0. Okay. And you need to use the definition. Remember, I need to pick the function calculated uh, plus some epsilon variated at the point y. Okay, so delta of x minus y minus the original functional divided by epsilon. In the present case, we have the limit where epsilon is taken to be 0 in the end. The functional is an integral from minus infinity to infinity. I am integrating over dx phi of x plus epsilon delta of x minus y if the interval is from a to b, a and b not infinity, not going to infinity. Of course, this y must be considered inside the interval a to b. Okay, you need to variate the function in the allowed interval. Okay, so you have this for the first part here. You need to integrate the functional, which corresponds to the original function plus a small variation minus the original integral, which is the original functional in this case, and you need to divide it by epsilon. Okay, so notice that you have the integral of phi of x dx minus integral of phi of x dx, which cancels out, and you are left with just the limit of epsilon, which is a constant, integral from minus infinity to infinity, the Dirac delta of x minus y integrated over all the values of x, summed over all the indices, okay? And in the end, you divide by epsilon. Taking the limit, epsilon going to 0. Notice that this epsilon cancels out, and the integral of Dirac delta over the entire space is 1. Oh, all right. This is the same, or this is analogous. It's better to say that this is the analogous of taking the partial derivative of a function with respect to some of its arguments. Okay, so this is the analogous of a summation over the vector components, which I plug in here. Okay, in the case of a function, and the result is the same. But here I am calculating a functional derivative, which is the derivative of a functional, which measures how a functional changes if I insert a small perturbation inside the functional. Okay, this is it. So we have an interesting analogy here. If you're calculating df of phi 1, phi 2, and so on to phi n over phi j, okay, and this functional uh, is, let me write it this way, phi I here if I'm calculating d phi I over d phi j, only if if I pick up the same indices here, it produces 1, okay? The variables are taken to be independent. So, in the case of a functional derivative, the corresponding identity or the corresponding property is that if you calculate the derivative of some phi of x with respect to some phi of y, it produces a Dirac delta. Okay? Taking the same idea, the Kronecker delta becomes a Dirac delta in the limit of a continuum, or if you take indices from discrete to continuous variables, Kronecker delta goes to Dirac delta. If you have a function of a vector which is just the summation of phi j, the derivative of this with respect to phi j is just, let me use here I to not confuse you. Okay, so I'll calculate the derivative of phi j, the summation of phi I from 1 to n. Now I have summation of, because using this property, summation of Kronecker from I going from 1 to n, it produces 1 because I specify some j, but I sum over all the n's. At some point, I equals j, and in this case, this is 1 for all the other situations. I am running I from 1 to n. In all the other situations where I is not equal to j, produces 0, but when I equals to j, produces 1. So this summation produces 1. And in the functional version, this becomes a functional. Notice the change of notation here. F of phi, the corresponding to a summation is an integral from a to b, suppose. Okay, from a to b, phi of x dx, right? And the derivative becomes a functional derivative instead of j, I have y, which is a continuous index or a continuous variable or a continuous parameter. And in this case, it produces 1. So it's the corresponding equation for this one. If you have a summation of a components of a vector for the scalar function here, just sum over the components of a given vector, which is the argument of this function. You have as a derivative 1 because of this identity here. You have this result here. And in this case, where you consider functional derivative of phi evaluated at some x and phi evaluated at some y, it produces 0 in any situation where x is distinct from y. But it produces a Dirac delta or infinite if x is equal to y. Okay, and of course, the corresponding to a summation is an integral, and the corresponding to the partial derivative with respect to some of the vector components is the functional derivative with respect to a variation of the function of the argument at some y, and produces 1. Okay, this is it. you can demonstrate this property here using directly the idea of functional derivative. Okay, so consider that your functional here to demonstrate this, consider your functional phi of x is just phi of x. Okay, it's just this. This is the functional. You can plug into the definition of functional derivative. You arrive at this result here. Exactly this result here. Okay, so this is it. Now another example, very important example. And we can consider analogies. So suppose for scalar functions here, if you have f of some phi equals to the exponential function of a summation, okay, of some set of constants, suppose um, k dot phi, okay, some summation, or I'm using the notation of a scalar product. So k dot phi. K is some constant vector which has components k1, k2, and so on till we reach the dimensionality of this vector here, and therefore k dot phi produces k1 phi 1 plus k2 phi 2 plus and so on kn phi n. So this is just the exponential of k1 phi 1 plus k2 phi 2 plus k sub j phi sub j plus kn phi n. Okay, if you calculate the derivative of this exponential with respect to some specific phi of subindex j, it will produce the derivative of an exponential, and we know how to calculate the derivative of an exponential. You just need to move in front of the exponential that k of subindex j, okay, and the exponential repeats itself. So k dot phi, the scalar product. Okay, this is a common result encountered in the study of waves. You have a phase factor. Usually, this is the position vector in replacement of phi. This is the wave number. You have an imaginary factor here or whatever, but it's a common result. If you are calculating the derivative, the partial derivative of a exponential, which depends on some function of phi, and this function is linear on phi, you will have as a result the coefficient multiplying that specific phi for which you are calculating the derivative and multiplying the exponential. So this is for a scalar function, okay? For a scalar function which is an exponential here. Scalar function, what type? Exponential. Okay? Well, what is the functional analogous of this? The functional analogous to exponential of k dot phi, some function of phi, which has a constant k with respect to the components of phi, which is a constant vector here. The functional analogous of that is this. Exponential in replacement of a summation here, because this is a summation of k of j, phi of j. Okay, this is summation over all the j's from 1 to n, is an integral over all dx. K of x becomes j becomes a continuous index, phi becomes a function of this j, j becomes a continuous index. This is the analogous and the limits of integration without loss of generality. We will take from minus infinity to infinity. Okay, so this is the analogous. This is functional analogous to this equation here. So this is the functional which we are interested in consider. So if we calculate functional derivative here with respect to some y here at some point indexed by y, this variable y, it is corresponding to the limit where epsilon goes to 0. The functional evaluated k of x, phi of x plus epsilon direct delta of x minus y integrated over dx minus the original and you need in the end to divide by epsilon. Okay, you need to divide by epsilon. This is the calculation we need to do using the definition. But of course, you have the limit epsilon going to taking the limit of epsilon going to 0, 1 over epsilon. I will write it in front of everything. Notice that this is the integral of a sum, which is the sum of integrals. And the first integral, k of x times phi of x, appears in the last term here. So I can also put this into evidence here, k of x, phi of x, dx. And if I integrate this direct delta here, multiplying k of x, the direct delta, remember, this is a property of delta functions. If you integrate some f of x, delta of x minus y from minus infinity to infinity, or from a to b, where a is inside the interval, over dx, it produces f of y. So this way our f is k. I am integrating this delta with respect to x. I just need to replace in place of x, I need to plug in y, but this is a constant of integration, so I have the exponential of epsilon k of y minus 1, because I am putting the first integrand into evidence. It appears in both terms here. Okay, so I'm calculating the functional displaced by this epsilon delta of x minus y, or change it by this small amount minus the original, and I have this. But now this epsilon is taken to be infinitesimal, so I can expand this exponential as 1 plus epsilon k of y plus epsilon squared over 2 factorial k of y squared, and so on. But notice, I need to divide by epsilon. This one cancels that one. This one cancels that one. The second term is epsilon divided by epsilon. In the limit, it's just k of y. And the following terms are higher order in epsilon, epsilon squared, epsilon cubed, and so on. And when you divide by epsilon and take the limit epsilon go to zero, these terms, because of this epsilon squared divided by epsilon goes to zero, and all the higher order terms going to zero. So in the end, you have as a result k of y exponential of this integral. Okay, this is the result. You could consider the following. If you are calculating the derivative with respect to phi of y, just insert the multiplicative factor at that point, y, and repeat the exponential. This is the analogous. This is the functional analogous. Okay, so this is the result. Notice that you could use the analogy here, just to end up with this lecture. You have a scalar exponential of summation over j, k of j, phi of j, or I was using I here. I'm using I here. So this is our function of the vector field phi. And I am calculating the partial derivative of this function with respect to some phi of j. It produces just the multiplicative constant at that j point and repeat the exponential, summing over I, the constants, k of I times phi. Now we have a functional, which is just an integral, because now k is indexed by a continuum, and also it is the phi from a to e, which could be taken as minus infinity and plus infinity, no problem with that. And if we calculate functional derivative of that, with respect to phi of y, it produces a function here. Notice the analogy or the resemblance here, k of y, and the exponential, which is the original, exponential. Okay, so this is it. A functional can be considered the limit where the argument, the input of a function becomes a vector which has infinite components, and the directions of this vector space varies continuously, and each of the directions are orthogonal to each other. Okay, just like in a continuous Hilbert space. So in this case, you replace a discrete by a continuous, but the results are very similar. Okay, I'm finishing here. There are lots of results to be obtained or are discussed in these cases, but I'm finishing here. See you next time.